ready when you are. Yep.
Hang on just a second. Okay. So this is Ivan Perez, who's going to talk to us about fault-tolerant functional programming, functional reactive programming. So again, it's functional Perl. Take it away.
Thank you. Thank you all for sticking around. It's right before lunch, so I really appreciate it. I'm here to talk about fault tolerance and functional reactive programming. And in particular, I'm interested in modeling satellite systems and autonomous vehicles and aerospace, and trying to understand how different kinds of faults can affect these systems. So the problem is the following. We have a satellite in space, and it needs to maybe stay in orbit, maybe avoid other satellites, maybe perform a mission. And you model this, and you prove that everything is correct. And so long as the hardware behaves exactly as you expect, that's great. But sometimes systems fail. Sometimes signals are corrupted, and then your system doesn't work anymore. So the questions that we're trying to answer is, what happens when these components fail? If we model this using a reactive framework, what happens to this whole system when something fails? And also, how can we understand what happens, and can we provide any kind of guarantee? Can we use the type system to provide any guarantees? So the abstraction that we use to model this is called a monadic stream function. And it's very similar to a stream function, but it incorporates a monad. And we use, this is just a model implementation. It's not the way that you should actually implement them. But it's just so that you truly appreciate what happens when you use different monads and why the type signatures work. So this is the model implementation. And the idea is that you process one sample, one input sample of type A, and you produce, in a monadic context, an output of type B and a continuation. And you use this continuation. Oh, there's an M missing here. You use this continuation to process the next input sample and produce the next output sample in a monadic context, and so on and so forth. So you kind of unroll this stream function. And there's a few things that are important about it. One of them is that everything is explicit in the types, meaning there's no hidden side effects. There's no I/O under the hood. And this is not necessarily true for many reactive, functional reactive frameworks. They hide I/O, and here everything is explicit. So if the monad is pure, your program is pure, and it's referentially transparent. And the other thing is that you use a limited language to construct them. So this language guarantees that you remain causal and performant, and there are no inherent leaks, which was historically one of the problems with functional reactive frameworks. This is not FRP, by the way. This is F, RP. So far, this is just the reactive framework. There's a difference because there's no time yet. Time is implicit, and it's just the natural numbers. It goes 1, 2, 3, and so forth. But it doesn't appear explicitly there. And part of this work is based on two papers that were presented. This was presented at the Haskell Symposium in 2016. And then there's a paper based on this that was presented last year at ICFP about testing. And what it shows is that if the monad is pure, then you can reproduce your tests perfectly. It's really referentially transparent, which is not necessarily true for reactive systems, and especially not for interactive applications. So the API that you use is the arrow API. These are arrows. Monadic stream functions are arrows for a given monad. So you can compose them. You can lift a pure function. You can put them in parallel. And you can also lift a Kleisli arrow, which means that you can lift something that has side effects at every sample. And this is what we will use to add fault tolerance information to reactive programming. So you can just lift a pure function that adds 1, and that means your input stream, you just add 1 unit to it and move it up. You can have the side effect of printing the output, printing the input, and then you can put them both together. And that means you first add 1 to every input sample, and then you print it, and then you continue processing input samples. So this is most interesting when you combine it with different monads. And this is really, really exciting because we get a lot of frameworks for free. We get classic FRP, we get ROS FRP, all for free by using just different choices of monads and inputs and outputs. So if you use the reader monad, then that means you have a shared environment, right? Because you can just pass an R or an environment along, but it's piped through for you. So that means you don't need to make it an explicit output and an explicit input and manually pass it through, which saves a lot of time and a lot of work. Another thing, so one thing that you can use this for is to pass the time. So you can pass the time in an environment. And in particular, you can pass the time since the previous sample. And this gives you Yampa's arrow. Sorry, this gives you Yampa's arrow, signal function, sorry. And this is more or less how it's built. It's optimized, but Yampa is implemented more or less this way, which means that you can get Yampa for free by just picking the right monad. And we have an API-compatible implementation of Yampa on top of this framework. And just in the Cabal file, we can just pick one or the other and recompile again and put it online. So in the same way that you can put something in the monad stack, you need to be able to remove it. And usually removing means that you either affect the output or affect the input stream. You require more inputs, more outputs, or you require extra monadic stream functions. So in particular, for example, we have running functions to provide an environment with every sample, and then it's passed through. And we have running functions to obtain the log in a writer monad. And this is actually what we're going to use for the rest of the talk. But there are other monads, especially control monads, that give extremely interesting effects. For example, the either monad. So if you plug in the either monad, this is the signature of the step function that you get, then you get one input and produce, maybe you're left with an E, or you continue processing data and producing data, which means that they terminate with a result. These are tasks in Yampa. And these, I think, are also base of the work of monadic functional reactive programming. So we get this for free by just picking the right monad. If you use maybe, then you get termination with no output. If you use lists, then you get parallelism with broadcasting. These all require specific combinators in implementations like Yampa, and we get them for free. So the problem that we tried to study was we have these monadic stream functions, and they model data processors and signals and sinks, and we connect them all together, and how do we understand what happens when something goes wrong? So this is the implementation of the system that you see on the screen. And the idea is that you have a satellite, and you're gathering information from a star tracker and IMU, and it's giving you more or less the acceleration of the satellite, and it's giving you the position of the satellite. And what you want to do is you want to orient it the right way. And this is really important because if you orient it the wrong way, you could end up moving the wrong way, or you could also not be able to perform your mission, or you could damage your equipment. If you point some sensors to the sun, you damage them permanently. So this is really crucial. And the implementation just says, these are the signals that I have. So I get for the input to my system the desired orientation of my satellite. And I start producing, I get from the star tracker, I get star information. From the IMU, I get inertial information. And then I put them all together, and I calculate the actions that I need to send to the actuators. And that's what I return. So that's the implementation, more or less, of the green box, green area. And yeah, just the things in the middle are the monadic stream functions. So these are, in this case, the star tracker is a monadic stream function that doesn't need any input, and it's giving you data. So is the IMU. And the calculate actions are monadic stream functions that are processing the input information from the stars and the desired attitude and giving you the actions. And just one signature, that's the signature of the monadic stream function for the star tracker. So how do we add fault tolerance to all of this? And it all relies on picking the right monad. And in this case, we're going to pick something like the writer monad. And the idea is that we're going to, this is the simplest example. It's not what we're actually using in practice, but it's just so that you all get a feeling of how simple it is and how just picking the right monad gives you nearly everything. So the idea is that we have a writer-like monad that allows us to tag values with some kind of certainty, right? So it just pairs two values, and then we can lift some kind of value inside this monad just to say that something has a specific reliability, a specific certainty, a specific fault information. For example, we can have a certainty that something works between 0 and 1. And then we pick the right monoid, and we pick 1 for when we don't know something, or we're just processing data, so the mempty is 1. And we just multiply certainties as we go along. And that means that we can just tag the components with a certain, well, certainty information. So we pick the original star tracker, and we just say, well, the information that we get from it is actually slightly unreliable. It's 0.9 reliable. And the only thing that we need to change, the other thing that we need to change, is the signature. And we need to indicate that this monadic string function is no longer fully polymorphic on the monad. It's just, it has fault tolerance information, and it carries certainty. And then we need to make 2 changes to the main implementation. This is the implementation that you had so far, and we need to use the new monadic string function that has certainty information, and then we need to change the signature. And that's it. And everything else has default certainty as 1. It seems to be working, so that's the only potentially faulty component. And then when you run it, and you say, well, run this whole system and tell me the certainty of, for one step of simulation, it tells you 0.9. You use data from one sensor that is uncertain, and that's your overall reliability. So you can do this for other components. You can add the reliability of 0.99 for the IMU, and then you change the implementation accordingly, and when you run it, it starts giving you lower values because it's multiplying the reliability. And the next question that we have is, okay, so now you can tell us that something is wrong, and you can give us a metric. And the question is, what can we do about it? And can we see how different fault tolerance mechanisms allow us to recover from these problems? And the default fault tolerance mechanism, when something fails, you just add another device that implements the same function. And then you compare the values to see if one of them is wrong, and maybe you could transform the output into a maybe, and at least you signal that the value was wrong. Or you could have more than like 3 or more devices of the same kind, and then you just choose by majority, you choose the best value. So essentially that means that to implement a star tracker that is fault tolerant to a certain degree, this is a very limited degree of fault tolerance, you need 3 star trackers. And when you put them all together, all you need to do is you obtain the certainty information from all of them and combine it. And combine it according to a formula. This follows similar things as probabilities, but it doesn't matter. It depends on how you're handling your own certainty information. Just combine it. And then you obtain the actual star tracker information and combine it. And then you put it back, and you're done. And then you go to your implementation and replace the components, and then you have a more fault-tolerant component. And when you run it, the certainty went up. So that's it. That's the main idea of the paper. But there's a lot of power that comes with it. So picking different monads gives you a lot more information about what's going on in the system. You can use a probability monad, and then you start getting outputs with different probabilities. So the only thing you need to change is you implement the faulty star tracker in a different way. You change the signature, right, from the fault tolerance monad to the distribution monad, I guess. And then you run it, and you get different outputs with different probabilities. And you can start asking questions such as, what's the probability that my value will be correct or will be what I expect, and so on. And this is just by picking the right monad. There's nothing more. You can also have fault models, and a fault model is just a classification of the kinds of faults that your system may have. And this one and the next one are the most interesting ones for us. And these are the ones that we're using. And the idea is that you tag the information that you get from different sensors and that you process with the reasons why systems could fail. And then you add that information to your monad, and when you run it, you get an output, but you also get an explanation of all the reasons why it could be wrong. And the other thing that you could do with this, which is a lot more powerful, because here you have to run it, and maybe you just run it with the wrong input that didn't actually trigger the fault, depending on how you implement them. But you could also put this at the type level. And this is all explained in the paper in the same way as, well, the previous point about the distributions is also explained in the paper. And if you put this at the type level, then you don't need to run it anymore to get an explanation of all the reasons why your system could be wrong. Just compiling it gives you a proof. And this is extremely powerful. So, in summary, what I just explained is that we can take a framework that is extremely simple, that allows us to talk about reactive components. And then we take an idea that is also extremely simple, which is a monad that implements probability distributions or just a writer to tag values. And then we put them both together and we start getting information about fault tolerance and about why systems can fail. And if we bring it to the type level, then we start getting proofs and guarantees. And these are not really strong guarantees because you could have made a mistake in the way that you identified the faults. This is also limited in some ways because you may want to analyze how many possible simultaneous faults you can have. So you need a very expressive, a lot of expressive information at the type level to be able to do this. But it can be done. And then, yeah, it becomes a proof at compile time, which is something that for many communities that do control systems, they're not so used to proving things as much as just testing things. And this is the part that I'm actually most excited about, which is how we're using this. So I told you that you can use a reader monad, and I told you that you can pass an environment. So how we're doing this now is we're injecting faults into our reactive models. And we have models of different satellites in space, and they need to avoid one another. And we implement a simple solution to this problem, and then we start injecting faults in the system. Faults about how they see each other, whether they can detect each other, whether they can talk to one another, whether propulsion fails, etc. And we obtain the fault rates that we use to inject faults from an environment that we pass along using a monad. And then we use temporal logic to encode properties about the system, such as that there should be no loss of separation, the satellites should remain in orbit and avoid each other if necessary, and so on. Not expending too much fuel, and so on. And then we give it to quick check. And then we start asking questions such as, is there any fault rate within these ranges that is going to make things crash? And the other thing, well, we're using this for two kinds of problems. One of them is UAV swarms. So essentially, these are swarms of satellites that need to perform a mission altogether, so we get redundancy from using different satellites, and we're trying to understand what we can say about consensus and the overall ability to perform the mission by just injecting faults in different satellites and seeing if there's an overall capability to continue operating. And the other is if we want to show that two satellites won't collide when they are in orbit, well, there's different ways that different things that could go wrong with the satellite, but it might not communicate with you and so on, and we're trying to understand whether we can say anything generally, and we can implement anything generally about the collision avoidance mechanisms that satellites use. And the last thing is that because we cannot really run Haskell on a satellite yet, we're starting now to use the functionalization to just create a first-order definition of the reactive network and then compile it to other architectures. Now, there's prior work on this in Copilot, and this is in some ways similar to other frameworks, but now we're also trying to generalize all of this and use this here so that we can then compile the implementation into maybe ATS or C. So that's pretty much it. Thank you very much, and I'm happy to take questions now.
Okay, we have time for a couple of questions. So I've got one from John Hughes. John asks, don't you need to keep track of whether faults are independent or not? For example, using two identical sensors increases certainty, but the output of one sensor twice does not.
Right. So you need to know this. You need to know if they are independent. And the way that these are designed in real systems is that you define something called a fault containment region. And essentially that means you have a sensor that is powered by a completely independent battery, is plugged to a completely separate network, maybe depending on the kind of sensor that it is and so on. And you try to isolate and keep the faults unrelated so that if one of them fails, the other one won't. At this point, this still requires expert knowledge, and there's nothing that the framework is going to give you for free to do this or not. But yeah, you can capture this information, but you're not going to get anything for free in this respect.
Okay. Phil Wadler asks a general question. He says, wow, very nice. So which satellites have been designed using Haskell?
I don't know. I can't tell you. No, I'm kidding. I don't think any. Not yet. We're still working on this. I mean, this is purely theoretical. We don't have the money or the mission to send this anywhere. This is something we're just studying at this point.
Okay. And one more question.
I'm hoping, if you got the money, though.
And one more question from Vasil. How is your system used in real-time in a real-time environment without any GC?
Without any what?
GCs, garbage collection.
Garbage collection. So that's a really good question. That's one of the reasons why we want to compile to other languages, because otherwise we cannot really provide any kind of hard time guarantees. And if we cannot do that, we really cannot put it in any kind of, not even in a drone probably, they wouldn't let alone a satellite. So yeah, but there's a talk at the Haskell Symposium on Thursday about how to extend reactive components with timing information so that you know how frequently they tick, and then you are forced to coordinate them right and to create buffers and to define buffers for coordination that they don't really guarantee, but at least express and capture some of that information.
All righty. Let's thank the speaker. And